Hi everyone, this video is part of Macquarie University's coding tutorials, and today we'll be talking about the concept of recursion and how it relates to the call stack and stack frames. First, we'll start by looking at a series of non-recursive function calls, which we'll call other functions to see more comprehensively how the call stack works. Then we'll look at a self-calling or recursive function. To understand how recursion works, it helps to understand the concept of the call stack and stack frames. In a very abstract way, imagine a stack of plates that you need to clean. Each plate represents a function that has been called, with the top plate representing the current function being executed. You must wash that one before the next one below can be washed. When a function calls another function, it is like adding a new plate to the top of a stack. These plates are called stack frames, and when the function finishes executing, in this case it would be once you've washed the plate, it is removed from the stack. Let's start understanding how this works by taking a look at this example. In our main method, we are using for ints to simulate 2 points, each with an x and y, and we want to find a distance between them. We won't be using our point class to avoid overcomplicating this, as we just want to focus on the call stack. We then call a distance function, passing in the first point's x and y and the second point's x and y. We save the result of that call to a double variable called d, and then print it to the console. Inside the distance function, there's a whole bunch of code that computes the distance by using the int that have been passed in. The details of how the distance is calculated is not important for the purpose of this video, but just notice inside the distance function there are two other function calls. One to square, which is a function that also exists in this class. We can see down here that the square function takes in an int parameter and multiplies it by itself to compute the square. The other function called in distance is the square root function that comes from the math library. The function has code inside that will be able to compute the square root of the number that we pass as a parameter. Let's now trace how the stack frames are added during the execution of the program. At any of the steps, feel free to pause the video and rewind if you have any difficulty following along to make sure you understand what is happening at each step. So let's begin. First, when we run the program, main is invoked by the Java virtual machine. The main method is placed on the stack to signify the start of the program's execution. Note that the parameter is an empty string array because we're not passing any arguments into main. To see how we can pass strings into this parameter, feel free to rewatch the command line video at the start of this series. Variable declaration doesn't affect our call stack, so let's skip to line 9. Here the main method calls the distance function with 4 arguments, 1, 3, 6, and 5. This creates another entry on the call stack with distance as the active function. Next at line 17, within the distance function, another function call is made to square with the argument of 6 minus 1, which creates a third entry on the call stack with square as the active function. We jump to line 25 to resolve the square function call, which returns the value of 5 times 5, which is 25, to the distance function. The entry for square is then removed from the call stack, and distance becomes the active function once again. We don't go back to the start of the distance function, but rather go back to where we left off, just under the first square function call. At line 18, the distance function calls the square function again with an argument of 5 minus 3, which is 2. This creates a third entry on the call stack with square once again as the active function. Again, we jump to line 25 to resolve the new square function call that has been added to the stack, which returns the value of 2 times 2, which is 4, to the distance function. The entry for square is then removed from the call stack, making distance the active function again. We resume at line 18 within the distance function, and a call is made to the math.squareroot function with an argument of 25 plus 4, which is 29. This creates a third entry on the call stack with math.squareroot as the active function. We can't see the square root function here, but we know it returns the value of 5.385 to the distance function. That is the square root of 29. The entry for math.squareroot is then removed from the call stack, and distance becomes the active function once again. We go back to line 22 of distance and return the result value, which was 5.385, to the main method. The entry for distance is then removed from the stack, and main becomes the active function. The call stack once again grows the same way when we print on line 11, but we will skip it here. Finally, the main method terminates and is removed from the call stack. With no more entries on the call stack, the program is finished executing. Now that we've manually traced the control flow, you may find it useful to restart the process but actually run the program and use the debugger as we've covered in earlier videos. Make sure to step line by line to reinforce the process of stack frames being added to the call stack. It's important to understand that the topmost stack frame has to be resolved in order for any stack frames below to be completed. Now what happens if a function calls itself? At this point, we might ask ourselves why we will do this. Although it may seem counterintuitive, let's first understand the how and we'll see the why in upcoming examples we will work through. Here is an example of a self-calling function in Java. The function will be called again, but each time a number lower by 1 will be passed. So, for example, if we call self-call 4 will be added to the top of the stack, and after that, self-call 3 will be added to the top, and self-call 2 will be added, and so on. Each function call won't be able to be resolved until the one above it on the stack is resolved. But how do we ever resolve a function call if we continually keep adding more without stopping? Well, this creates a stack overflow error that we briefly mentioned in our video on errors and warnings. This leads us to the number one rule of recursion. We need a base case. Just like how when we have a while or for loop and repeatedly perform actions, we have a condition that tells the program when to stop. So let's say we want to stop as soon as n is 0. We need an if condition that says if n is 0, return. To be safe, in case anyone passes in a negative value to begin with, we can make the condition say if n is less than or equal to 0, return. Since it's a void function, we don't need to write anything after return besides a semicolon. This means return nothing. So once self-call of 0 is called, it will return and do nothing. Then self-call 1 will be able to resolve, then self-call 2, and so on until self-call 4 resolves, returning control to the main function. Since there is nothing else in the main function, the main method resolves and the program finishes executing. Now that we can say that this function will print a message called with n for each value of n, starting with the value passed as a parameter and counting down to 1. Similar to how we did with the previous non-recursive function, have a go at drawing how the call stack changes between function calls. In this video, we went over how the call stack works during function calls and the order in which stack frames are added to the call stack. The goal was to feel more at ease with how non-recursive functions work before moving on to self-calling functions. We then introduced recursion by taking a look at a simple self-calling function and how its execution appeared on the call stack. In the next video, we'll apply our understanding of function calls to a recursive problem and the approach we'll need to design the algorithm. See you there!